Everyone. So today we have Pouya with us, who is a graduate research assistant at Robotics and Mechatronics Laboratory. And today he will talk about human force estimation in physical human-robot interaction, which he presented this work at pHRI last year. Yeah, the stage is yours, Pouya.
Okay, hello again, everybody. Today I just want to talk, as Aykut just said, about how to estimate human force in pHRI, or physical human-robot interaction, with deep learning. This, of course, is unpublished work. The paper you saw in the related publications part is the result of our previous experiments, which didn't actually involve machine learning, but I'm using their data, and that's why I just mentioned that paper in the related publications part. But so far we are actually relatively at the beginning of our research, so we have a lot to do before it becomes published. But of course, let's continue. Aykut mentioned it briefly, but here I am again. I am Pouya Niaz. I am an MS student in the Çağatay Başçıvan's Robotics and Mechatronics Laboratory. I joined the lab since, well, October, actually. Now, here's just a quick outline. So first I want to talk very briefly about physical human-robot interaction and why it's important. Then very briefly, I'm going to talk about adaptive admittance control, which of course is always one of our ultimate goals in pHRI. And then I'm going to talk about human force estimation and how we can use it for adaptive control. But of course, human force estimation also includes subtask classification. So I'm going to very briefly touch on that as well, even though that's not our focus. Then I'm going to cite my current progress and just tell you briefly about my future plans. And that's it. So the reason physical human-robot interaction, or actually human-robot interaction in the first place, is important for us is because we have come to realize in the last few decades that robots, as precise and robust they are, don't actually have the cognitive abilities of human beings. They're not as intelligent. They're not smart enough to think for themselves. And humans, on the other hand, as intelligent as they are well, mechanically inept and very clumsy, and they're not very precise. So we actually understood that the combined capacities of humans and robots together leads to very interesting opportunities and can cause, in many cases, for the tasks to be executed much more efficiently, actually, because we're combining the precision and robustness of robots with the intelligence of human beings. This combination has already led to many interesting applications so far, ranging from assembly to accurate positioning, from surgical assistance to transportation of heavy objects, and also to rehabilitation, of course. Now, with manufacturing being one of the most prominent applications of pHRI, that's what we've been focusing on lately. You see, in manufacturing, there are very fast and small repetitive batch processes, such as welding, soldering, drilling, particularly of small objects. And they can't really be automated. It's very impractical to automate them. They need to be done by human beings. But then again, as we said, human beings are mechanically not very accurate. So we need the precision of robots to perform them. And that is where pHRI comes in, actually. Now, in our lab, we have set up a very simplified version of this drilling application. It's one of the applications of pHRI in manufacturing. And we've built a simple setup in our lab and tried many experiments with that. And this is the setup that we have. There's a collaborative robot, or cobot, as we call them. There's a tool attached to it. In this case, it's a drill. The tool has a handle for a human operator to grab. We have some force sensors to measure the interaction forces between the human and the environment and the robot and so forth. The human operator, in this case, is wearing an AR goggle. It's a Microsoft HoloLens for convenience and display. It's not actually a necessary part of pHRI. It's just for user convenience. And we have a workpiece here, a flat wooden workpiece representing our environment. And we have a one-dimensional linear motion on which the human operator is going to grab the robot and just move forwards, drill a small hole in the workpiece, and come back. It's a simple linear pHRI experiment in 1D, but well, it tells us a lot of information, and it's actually very useful to us. Now, for the robot to be compliant to human input, in order for the robot to basically move when you push it, you need some kind of a control system. That is to say, an interaction controller that takes an input from human and environment and whatever, and turns it into robot command so that the robot can follow your intentions. One of the most frequently used controllers in this regard is the admittance controller, and it's also what we have used. It's basically just a PID controller that takes in the interaction force. This is basically the resultant force of human and environment and everything else that is interacting with the robots, and turns it into a reference velocity that is given to the robot to follow. And as you can see, it has some parameters such as M and B. We call them mass and damping. And according to how you set these parameters, the behavior of the robot is going to change. For example, this B here is damping. Usually if it's high, the robot is slow and sluggish and kind of hard to move. By contrast, if it's low, the robot is kind of fast and loose and even slippery. So these parameters are very defining on the behavior of our system. This is a very simplified diagram, a closed loop diagram of our system. You have human and environment interacting together and with the robot. And they generate some kind of a total force, which of course is always low pass filter because it's very highly noisy. This interaction force is led to the admittance controller, which produces a reference velocity for the robot to follow. And according to the behavior of the robot, again, human and environment input some force and the loop goes on. Now, let me actually show you a very, a very quick example of what we've done. It's just a very short video. Here you have our setup, the cobot, drill, force sensors, workpiece, the human operator, and so forth. This black box, the diagram here, you can easily ignore. It's just showing how we are changing some parameters, but it's not the focus of our talk today, so you can safely ignore it. So at the first, the robot is just stationary. Nobody's touching it. It's not moving. So this is basically the whole system is at an idle state. Then the human being grabs the robot and starts moving it forward in a 1D free motion in space. You're not interacting with the environment yet. It's just human moving the robot. The motion goes on until the human being and the robot make contact with the environment, which in this case is a wooden piece. And at this point, the dynamics of the system change, and you are basically in a different state. You are, let's say, in a contact state with the environment. At this stage, human and robot together are interacting together, and the human being is pushing the robot into the drill, into the wood to drill a hole in it. This is the view from the HoloLens AR goggle. It's just for convenience for now. It just tells us how far we are from the workpiece and how deep into the workpiece we have to drill, for example. This black box is just a diagram of comparison of different controllers. We can easily ignore it for now. Again, the same thing happens. So as I said, in this particular pHRI scenario, and actually in most pHRI scenarios, we have different stages. We're calling them subtasks. In this particular example, first we are at the idle stage, and then we are at the free, we're just basically moving the robot freely in space. But when I say free, it's constrained to 1D, but the point is we are not contacting any environment yet. And then finally, we have an active interaction with the environment. And the environment is also putting some forces on the robot, the robotic system as well. Now, when we are at idle or free, ideally we would like the robot to be, fast and loose and very compliant and responsive to us. Conversely, when we are in the contact stage or subtask, we want the system to be very rigid and stable and very, very slow, so that we don't break the robot or the environment, and we can more efficiently control what we do with the environment. And therefore, we want different control parameters, because depending on the control parameters, this robot can be rigid and sluggish or fast and loose. So we want different control parameters for different subtasks, and that calls for an adaptive admittance controller. So the point is, first we need to detect the subtask, which stage of the experiment we're in, and then adapt our control parameters. Now, for performing subtask classification, let's call it, this is a sample time plot of an experiment very similar to what you saw the video of. At first, the blue ones is velocity, the red one is human force, and the green one is environmental force. We've just measured and recorded all of them. At first, we are at an idle stage, everything is zero, and basically just noise. In the free motion subtask, the human being just speeds up until some extent, and then by getting closer to the environment again, we slow down a bit. And as soon as contact is made with the environment and we go to the third subtask, that is to say, velocity and interaction force very, very quickly diminish and stay very close to zero, because the motion is very, very slow as long as we are performing drilling. Whereas human forces are very high, because the human being is the one that's battling with the environmental forces and trying to move the system forwards. Now here, if you want to do subtask classification using only, for example, velocity and interaction force, it's not going to be very successful, because, for example, in idle and contact, velocity and interaction forces are very close to zero. So that's not going to be very helpful for us. And also, human being is the one that decides what subtask we are in, and human operator is the one that defines the subtask, actually. So we need to take its force in order to be able to accurately and efficiently detect the subtask. So human force is necessary for subtask detection, or let's say efficient subtask detection. Now, the big problem that we have, and this is actually the key point for my research, is that we don't have human force. Well, here we have human force because for research purposes, we're recording it. But typically in pHRI, you just have an interaction force sensor. It's usually expensive and well, impractical to include another human force sensor. So we don't actually have it, and we don't want to have it, which means we have to estimate it. And that's where my work, human force estimation, comes in. Now, this human force estimation actually also has many other applications generally in pHRI, but we'll talk about that later, actually. Now, what I said about human force being necessary for subtask detection, the opposite of what I said is also true in human force estimation. And you have some parameters, some measurements, such as velocity and interaction force and so forth. But again, for example, in idle and contact, you have very similar velocities and interaction forces. So how are you going to detect, how are you going to estimate human force? You need to know which subtask you're in so that you can estimate human force. So that here, for example, you can decide that even though velocities and interaction forces are low, human force is high, which means subtask is necessary for human force estimation. So here, this is basically the opposite of this one, which means we are going to need some kind of a loop so that human force is used for subtask detection, and conversely, subtask detection is used for human force estimation. So we're
something.
Yeah.
Can you for me it is not, I'm sorry, I'm not familiar with the domain. It's not clear
of course.
And what is not given. Can you record such observations in large quantities?
For velocity and interaction force, yes. Velocities are always recorded from the robot's own system. And we already have a force sensor, which is interaction force sensor, and we always have this. But the problem is in real-time applications, we just don't have a human force sensor.
Okay.
We did have human force sensor because we were doing research and we recorded it. But normally we don't have human force sensor, and we don't want to have it because it's expensive, it's additional costs, and it's impractical because every time you change the tool, you have to change the sensors and the handle and so forth. So we don't actually want to deploy it.
So what you want is subtasks, but subtasks require human force.
Yeah.
Without human force, you cannot identify subtasks. Is it correct?
Yes, you can, but you never have more than 50 or 60% accuracy because velocity and interaction force are very similar here. Here, actually, our wooden piece was very harsh, so these figures here are not very close to zero. But especially if your environment is kind of smooth or soft, like flesh, for example, human flesh, these values are actually going to be very, very close to zero, much closer than they are here. So it's going to be practically impossible to detect subtasks from these data alone.
Okay, thanks.
Welcome. So basically, we need to do two things simultaneously, separately. We need to perform subtask detection and human force prediction simultaneously, actually. Subtask is needed for adaptive control, and it needs human force data. Human force is needed for subtask detection, but it itself, one of its inputs, need to be subtask data. Now, if you have measured human forces, we know that you can train a model to do a subtask detection because this has actually already been done by one of our own students, one of our former MS students in the RML was Utku Erdem. He was also a Barış Hoca's student. And he performed similar experiments in, albeit slightly different environments to ours. And he performed successful subtask detection and also adaptive control from subtask detection. But the thing is, he was using human force. He was using measured human force. And well, that's where the problem comes in, and we don't want to do that. So because he was successful, and we also tried it with our own system, and we were also very highly successful, we actually found out that subtask detection is kind of easy, that is to say. We won't actually be focusing on subtask detection a lot because it's been done before. We just wanted to see if we had labeled known subtasks, whether or not we could train a model that could predict human force. And well, the answer turned out to be positive. After we train a subtask classifier and the human force estimator separately on, let's say, measured and known data, we just need to put them in a loop like this. So we have a human force estimator, which estimates the force, and you can record this force or use it for other purposes. This human force goes to a subtask classifier whose input also is interaction force and velocity, because both of these are actually measured and we can easily use them. And the output of the subtask classifier is an input again to the human force estimator, which also takes in velocity and interaction force and also control parameters, because control parameters have kind of very large effects on human force we've seen. And we just wanted to see if we deploy such a system, whether or not it could be successful or what kind of performance it would have. Now, coming to our training efforts, previously when we were performing experiments for the pHRI paper, the pHRI paper's objective was something completely different. It was just, they just proposed another controller. But we do have many experimental data which we can use. In those experiments, we had 7 subjects, human subjects. We had 3 different sets of control parameters to try on. And with each of them, each subject performed 4 trials. So we have like 84 experimental trials in total, amounting to about 560,000 time samples in total, in its entirety. This is the entire size of our data set that we have, all of it. Now, with subtask detection, especially because our definition of subtask was relatively easy, it's just idle, free motion and contact. Utku actually used a much more complicated definition of subtask. He divided into 5 subtasks instead of 3, but he was still successful. And with 3 subtasks, we're going to be even more successful. So even we tried this, and even with a relatively simple multi-layer perceptron with just 1 or 2 hidden layers, we were successfully able to detect subtask using a force measured human force. We just achieved with different hyperparameters about 97 to 99.6% accuracies, our testing sets. I'll share the range of architectures that we used later on. And when we looked at the data to see where misclassifications came from, we realized that it was just simply delayed or premature transitions. You know, when you transition from subtask 1 to 2 or transition from 2 to 3, there was just usually between like 0.01 second or 0.1 of a second delayed or premature transition with our subtask classifier. And that's really all the error that there was in this, for example, accuracy. Force estimation, however, has already proven to be much trickier, well, slightly more trickier. So far, I've tried multilayer perceptrons and LSTM because they're very popular in pHRI, actually, even though we can also try other things. But so far, I've only done MLPs and LSTMs. And this is the just a combination of all my results on all the trials of all the subjects, actually. These bold lines that you can see here are means, mean values across the time among the different trials of different subjects. And these shaded areas are standard deviations, again, among different trials of different subjects. The time domain is, of course, normalized and interpolated, so they all have equal length. And these blue ones are actual data and red ones are predicted data. And as you can see, performance is actually more than acceptable, especially in the idle and free subtask. It's actually near perfect. And in the contact subtask closer to the end, there is some error. But well, actually, this can also be improved. We haven't done a very thorough hyperparameter search, but this can easily be improved. And we are actually doing it. It's ongoing. Our RMSE values usually ranged, depending on our hyperparameters, between like 0.9 to 2.5 newtons, both for MLT and LSTM, which is not bad, actually, considering the fact that forces go as high as 32 or sometimes even 40 newtons. It's really not bad. Our R2 scores were somewhere between 0.95 and 0.98, which again, it's not bad at all. Now, this just for your information is the range of hyperparameters and training options that I have so far used. Of course, I haven't actually explored all of this hyperparameter space, which is actually impossible. But well, we're still doing hyperparameter search trials for optimization. Now, usually when we try to get anything done in pHRI, especially using machine learning, we have two very big obstacles. One of them is the stability of the control system. So we can't really change, control parameters very quickly. The other one, which is relevant to me, is, well, real-time implementation. So whatever model I use for either subtask classification or force estimation, it needs to run in real time at a reasonable frequency. And the higher, the better. So realistically, we can't actually just go ahead and make our models just infinitely complicated. We have to try and keep them as simple as possible with acceptable performance. So most of the bigger models, such as these bigger LSTMs here, we have tried them and we will try them just for training to see how they work. But realistically, we probably will try not to actually implement those really bigger models in real time. You can just take a quick look. These are the things that I have done so far.
Can you explain the sequence part? Like what is given, what is estimated in this part, in seconds or milliseconds?
In Hojam, I didn't hear you, the last sentence.
I was just asking, like, what is given and what is, sorry, what is predicted in the sequence part?
In the sequence part, we have, well, our inputs are sequences rather than instantaneous data. And their inputs are just basically the inputs of these models that I showed. Just let me go back to the, oh yes.
How many milliseconds and like?
Our sampling frequencies was 500 hertz when we were performing those experiments. And so our samples have a 2 millisecond distance from one another. And we are using, for example, a history of, that is to say, history of interaction force, history of velocity, and also history of either measured or predicted human force. It's just a buffer, it's just a moving buffer, moving along time for all of our experiments, basically.
And how far does it go? What's the size of the buffer, for example?
The size of the buffer I have actually mentioned here. It was usually between 10 and 100 samples.
Oh, okay, that's what you
which is, yeah, which is equal to between 20 to 200 milliseconds. We don't really want to put more than this because, again, it will make the input size bigger and make computation harder and slower. So we didn't use any more than 200 milliseconds, but our performances were actually acceptable so far.
And you always use the same LSTM for each of the subtasks, right?
Yes, so far that is what I have done.
So,
but actually,
okay, maybe you're gonna say the same thing, but this is similar to driving modes in autonomous driving. And what people do, driving modes, I mean, like going straight, turning left, turning right. What people do is they add branches for each driving mode. Depending on the high-level command you take, you use a different branch. So branch means the small part of the network. You have like a large base network, then it branches out to these high-level commands, in your case, to 3 subtasks, and each subtask has its own part where it can learn specific behavior, right? Because your subtasks have very unique behaviors within themselves.
Of course.
I think that kind of setting makes things a lot better for you.
Yeah, and we will actually, that's one of our next steps actually, in case you mentioned. Previously, I was trying these kinds of things with Utku's data, and I actually didn't use branching, but I used separate models, like separate MLPs entirely and separate LSTMs for different subtasks, because as you said, the dynamics are completely different. And it, as you said, it did actually work. It improved my performance. But here, as you saw in the previous figure, actually my performance was, especially if I'm not using exact force values, I'm just using the subtask data. I just want my performance to be good enough for a subtask classification. So for now, we just sufficed and just went ahead with it. But if I was very keen on increasing human force estimation performance, yes, that is very much correct. It would be good to use branching or even just train different models, maybe on data collected from different subtasks. We will definitely.
How is it branching different than like training different? I think that's what the Fatma Hoca is saying. Like branching means like training different models for each subtask, maybe.
Hocam, we have observations which are like very expensive to process, images, videos, right? So the processing of the raw image or video part is shared between the branches. They have like a complete CNN shared between different branches. And then when you try to estimate specifically the parameters for a branch, then you have like 2 layers, whatever, separate for each branch. It's a very small part of the network compared to the base part. Because of computation issues.
So kind of like a hierarchical learning model. Is that so? I mean, like.
Yeah, you can think of like,
So you have some layers for general purpose and then the sub layers for.
Exactly. It's a bit hard to train, by the way, but.
Nice. I mean, one issue in here is this: we need to execute this in real time, and we just need to keep the model as small as possible. That's one issue because the loop is running very fast, like 500 hertz is enormously high speed. So we need high speed to have stable interactions with the robot.
I see.
And, so whether we can run those models in real time, we don't know. So we're trying to, at this stage, trying to keep the model as small as possible to be able to run it in real time. That's one of our.
You're running on CPU, right?
Yeah.
Well, for example, with subtask classification, the physical response time of a human is usually between 150 and 200 milliseconds. So it shouldn't be any more than that, actually. The update rate of our subtask classifier, in the worst case, shouldn't be any more than 150 milliseconds. But actually should be much lower. The higher the frequency, the better. But it really shouldn't take any more than that. That's just the response time of a human being. It should be shorter than that, our update rates. Anyway, these are some additional observations. The reason I used a very low number of epochs is because my RMSE would just drop very, very fast in like, I don't know, maybe epochs and just basically stay there for the entirety of the training iterations. So basically there wasn't any difference between 50 epochs and 500 epochs, so there wasn't any point increasing it. And here is my regression performance plot with actual values and estimated values, and the equality line here. These spikes that you can see here and also here are actually momentary delays, actually. You see, there was a very small delay usually between the estimated and predicted human force. And these are usually just because of those delays, and also very, very small errors. These deviations from the equal line are actually very, very sparse. The distance between these consecutive tiny dots here is actually just 2 milliseconds. So these are all happening very fast and very momentarily. But most of our data is just on the equal line, and which kind of validates our relatively good RMSE and R2 scores. Additional observations I just want to cite is predictably LSTM performed better than MLP. And usually its RMSE values were, of course, depending on the hyperparameter, but usually between half or 0.7 newtons better than MLP. But again, due to real-time implementation restrictions, maybe it's not worth the complexity, probably, because MLP also produced the same results, actually, acceptable results. Those results were the combinations of MLPs and LSTMs with different hyperparameters. And also, I haven't actually performed any real-time benchmarking to see how fast or slow each of them are in comparison to one another. But I don't know, maybe LSTMs are usually very big and complicated. Maybe it's not worth the complexity, but we will test that and see that later on. Another observation, as I mentioned, was that in idle and free subtasks, performance was near perfect. But in contact, especially close to the end, there's this little error here. The error was a little bit larger close to the end. But it's not actually a big deal for us because, again, we're not using the exact force values for anything for the time being, for now. It just needs to be good enough for the subtask classifier. And it is good enough for subtask classifier. Now, if you remember, after training the subtask classifier in the human force estimator, we want to put them in a loop like this and just run it through all the experiments and see how they work. And I did this and run it on actually a separate cross-validation data, let's call it, unforeseen actually. And well, it worked. Firstly, and most importantly, I didn't have any divergence because, if the force estimation is wrong, then subtask classification is wrong. And this incorrect input can lead to an even more incorrect force estimation. And this error can just go on and just diverge in this feedback. But I didn't have anything like that at all, actually. And it makes sense if you think about it, because if my subtask classifier is performing at close to 100% accuracy, and intuitively, I can say that it's not the human force value itself that defines subtask, it's changes in human force, like how fast or abrupt it increases or decreases. That's what defines the transition between, for example, subtask 1 and 2. So the exact human force doesn't actually matter. So even though force estimation can sometimes be erroneous, especially in this subtask classification, performance is not affected all that much. As you can see, compared to a subtask classifier trained on measured human force rather than predicted human force, this one that uses predicted human force had like 0.3 to 1.5% drop in subtask detection accuracy. And this was just actually tiny little, sometimes fluctuations between different subtasks. And that can actually easily be taken care of using a filter of some sort. So that's not actually a big drop in accuracy for us. And that's more than good enough for an adaptive controller. Now, so far I've trained a subtask classifier, and I have used human force estimation for the sake of subtask classifier, and then for the sake of adaptive control. But closer to the beginning, I advertised that human force estimation can have other cool applications as well, but I failed to mention any. So these are some applications. you see, if we can estimate human force, then we can also forecast human force. And if we can forecast it, then we can use adaptive control with human force itself, actually, rather than subtask. So we can determine if the human force is estimated to accelerate or decelerate in the upcoming 0.1 of a second, for example, and then just adapt control parameters beforehand. So we can actually use human force directly for adaptive control. And also, let me just bring up the closed loop diagram. Here you have different blocks: admittance control, robot dynamics, low pass filter, and environment. These are all well known, actually, and they can very easily be modeled. Robot dynamics are usually derived from, I don't know, systems identification techniques and so forth. We actually have them. Admittance controller is known, low pass filter is known. The only unknown or hard to predict element in our entire pHRI scenario is human. And the only thing that human inputs to the closed loop system is a force. That's the only interaction between human and robot. So if we can estimate human force, then this human block, this human model is known. And then we can simulate an entire pHRI experiment. And then we can use that simulation for many purposes. You know, simulation with some bells and whistles can turn into automation. And also, if you can simulate an experiment, you can use, you can reproduce it with different conditions and use it for reinforcement learning. For example, we tried reinforcement learning for optimization of controller. Some people have done this, but well, for reinforcement learning, 50 or 100 trials usually don't cut it. We need many trials. We need 1 million trials, and we can't really do 1 million experiments. But if you can simulate the experiment, you can easily run that through something like this. And also, if you can simulate human force, then you can use some kind of a long-term incremental learning algorithm to personalize your controller for different people. So in real-time pHRI industrial settings, it's just 1 or maximum 2 people working with a robot for a long time, at least a year. It's not like different people are going to play with the robot every 5 minutes. And the robot, starting with a pre-trained model, can actually learn from the human being and just adapt to that very specific human being in time. So incrementally, it will learn to personally adapt to a specific human subject. And we can also use a very well-trained human model for that one also. Generally, to put a long story short, this human force estimation can generate an intelligent human model, which we can use, which actually opens up many avenues in pHRI. So in the future, first of all, I'm going to make an adaptive control scheme using subtask classification. Previously, Utku had also done this. I'm just going to deploy this with that feedback loop that I mentioned. Deploy it and test it in real time. So far, I've tested in just test data. Basically, I haven't actually tried this in real time. But since we are relatively confident that it will work because I just tried it on unforeseen test data and it worked. And then perhaps later in the future, I'm just going to look for other uses for human force estimation and a deep learning human model, that is to say. Those are my future steps. But for now, I'm just going to focus on adaptive control using subtask classification. And that's it, really. I am at your service, and thank you very much for listening patiently.
Thank you for your, this was really an interesting talk. So any questions from the
Actually, I'm not sure whether we have time or not, but I have 2 questions. Can I ask?
Yeah, sure. Go ahead.
Okay, can you go to slide 14?
Yeah.
Okay, I was following your talk very carefully, but I unfortunately didn't get the point where those spikes come from here in the right plot. Can you tell me again?
These spikes are, let me show you this plot. As you can see here, there's a very tiny delay between the actual and predicted force figures. This delay here is very small, but actually the difference is very high because the slope of the figure is very high. So a tiny difference of just 0.01 of a second here will turn out a vertical difference, a relatively large vertical difference.
Yeah.
And this whole process, and also here the same thing can occur, but this process has a very high slope, and it's just happening basically in a very short time. And that's where those spikes came from. And also these spikes are, let's say, regression noise sometimes, especially the ones that are very sparse, like this one or this one. Those are actually just, let's say, momentarily it just spiked a relatively high figure, the prediction, and that just momentarily produced a spike over there. So it's regression noise, let's say, combined with delay, momentary delays.
Okay, and can you go to the one to the last slide? I think the upper one actually. Yeah,
this one. Yeah.
So I didn't also get the point for the last section. So you said that we can actually tune some controllers based on some specific human user.
Yeah.
So how are you gonna do that? Just you let one human user try to work for a very long time with your control system, or what?
For developing such an algorithm, you mean? For developing, we could test it on.
I'm just asking for the exact underlying algorithm that you're going to implement for that.
I don't actually know because I haven't actually done many studies about long-term incremental learning or reinforcement learning, so I don't exactly know how we can implement this. But
you just tell me the whole concept. Yeah.
The concept is that.
One idea could be like making maybe robot be more proactive, depending on the user. Like if the user is not applying much force, like characteristically, he or he is not very much applying force. So maybe you can make it, if you understand that characteristic, then you can make it a bit more proactive. So, I mean, in here, like in some sense, robot is helping you, but it's not really proactive. Like it's not really doing something more than what the user is asking.
Yeah.
But it could be, like, that could be another step, for example.
The thing is, this deviation that you can see here, this shaded area, is standard deviation among different trials of different subjects, okay?
Yeah.
A large part of this relatively big deviation actually comes from different human beings, not different trials. So we've actually seen in our experiments that different human beings perform very, very differently in many pHRI scenarios. Some people are, they have bigger muscles, some of them have smaller muscles. Some of them are impatient and like to move fast. Some of them are very slow and careful. So the range of human behavior is actually very, very large, and they perform very differently in different tasks. And on the other hand, as I said, in real pHRI scenarios, in a factory or whatever, you're just going to have one person working on the same robot for a long time. Now, this is actually its most prominent example is our own, laptops and smartphones. They have very pre-trained algorithms in them, but every single time you work with them, it just learns something from you, specifically you, not any other human being. It just learns to adapt to personally you. It learns to recognize you. It learns to recognize what kind of a human being you are and what your behaviors are, and just learns to adapt to you personally.
So perhaps, over time, you are going to somehow change the parameters inside the block, which is named human plus environment. You are trying to change the parameters inside that model to make it comply with the specific human user.
No, we are trying to adapt the model itself. The model is the one that adapts control parameters. So we are going to, when I say we might, this is just an idea for now. The idea is that the model, the deep learning, the intelligent human model that you have is going to adapt itself in time so that it should have many other parameters. It's not just a normal MLP or LSTM. It should have many other features, and it's going to try to update those features every time a person performs an experiment to find out what kind of a human being that person is. Is he strong? For example, is he or she?
So you have to define some other hyperparameters or something like that and try to identify them? Actually, not hyperparameters. You should just understand. You should define some.
Of course, yeah.
Yeah,
Excuse me, Professor, I didn't hear you.
Yeah, I'm saying that it should be just, it's not just a parameter modification, like that's what he's going to be doing, but like if you're going to make the robot more proactive, it has to be more than that. For example, if the person is trying to drill a surface which is very hard to drill, maybe, and he's not applying enough pressure, enough force, then robot has to understand that and then maybe apply some force by itself, right?
So
I mean, like that.
The intelligence system has to understand, get some perception about the material, how the human is going to act or something.
Right.
You have to add
it has to learn that from the human behavior, that person's behavior. Like, for some people, that task might be easier. They can apply larger forces to open a hole for a hard surface, but for some people, it may not be. So if he can figure out that somehow, then it can take a proactive role and then like apply more pressure on the surface by itself, for example.
And it should be something much more complicated than just an MLP or a DSTM. It's an intelligent, maybe incremental learning algorithm or something else. We can just do experiments and just simply come up with a very simple heuristic to update, model. It's not like that. It's much more. It should be much better.
Thank you so much. Thank you.
So Pouya, I have a complementary question this time regarding this reinforcement learning setting. So there, the most crucial thing is to design the reward, right? So in that case, that reward may be just completion of the task. So from these discussions, that might be hard to get any meaningful signal because I think there are very micro events that you want to capture. One thing that came to my mind, I don't know whether this is too naive or not. Like, for example, we are talking about human-robot interaction. Maybe you can use language as well. Like, for example, the operator might say, not so fast or a bit more. That can just include like more precisely located signals to direct the robot. Maybe. I'm happy to hear your opinions.
Hocam, our students previously tried reinforcement learning. I think the reward function was the effort. Hocam, am I right? Do you remember what
So the goal was like we spent approximately 2 or 3 months. I think your idea is very interesting, by the way. It may help us to solve the problem. We haven't been successful in reinforcement learning. We're still, we didn't spend a lot of time, so it was like a side dish for us. We spent approximately 2 to 3 months, and our goal was whether the system can learn to, for example, adjust the damping by itself, rather than you mandate it somehow by identifying, classifying subtask, whether it can just learn how to adjust the damping. For example, like going from point A to point B, very simple task. So when you go from point A to B, you start from point A, accelerate, and then decelerate, and then you just want to come to the point B with a high accuracy. Very simple. But we quickly observed that you need many trials, and which is not very practical with the robot. We did like even 50 tries, and that wasn't enough. It wasn't learning. And another thing is like, human behavior of human subjects, as Pouya mentioned, is changing. Some people are, really very accelerating very fast at the beginning and slow down at the end. Some go like slow at the beginning and pay more attention to the accuracy at the end and things like that. So unfortunately, that was a hard problem for reinforcement, like asking the reinforcement algorithm. I think they use deep reinforcement, continuous reinforcement learning algorithm. It was a hard problem. So, I mean, typically as you know, in reinforcement problems, there's kind of success or unsuccess kind of criteria. And there's no such a thing in here as well. And the cost function for us was effort and time, for example, completing that task in time and how much effort you're doing to complete that task. And that's what we were trying to optimize. And it didn't work. And like, I mean, I think that system requires more input. That's what I'm thinking. And the voice kind of thing could be helpful. That's a very good idea. Like if voice edit, like the subtask identification, like voice edit, then maybe a system will understand that you have to accelerate, you have to decelerate. So learn where, at what time accelerate, decelerates kind of thing.
People have done this with gesture recognition, Hocam. Not language, but I've seen many papers that use gesture or posture recognition to something like what I could
maybe posture recognition. Yeah, that's another interesting idea. Where based on, because like as you lean forward more, that means you're maybe accelerating the robot. But even like, I think like that idea is very nice, Pouya. Like voice is very simple. I mean, we can ask the subjects to command the robot and maybe give like 3 or 4, at most maybe 3 voice commands: accelerate, decelerate, neutral, something like this. That may help. But if you guys have any other like ideas on reinforcement learning, we'll be happy to learn more about it.
This might be useful in autonomous driving. What works really well is people first train it supervised in a behavior cloning approach and then train reinforcement learning on top of that. They don't start training the reinforcement learning model from scratch because it's very slow and hard to train, as you said, and requires a lot of data. That's why like starting from a very good point for the reinforcement learning agent makes things a lot easier.
Yes, that's why this very good point, Fatma. That's why we have this motivation of estimating human force, because if we can estimate human force, we're going to be able to put it into this loop that you see in here. We have some models of robot, admittance control, human, and if we can also have some model of environment, maybe that's another issue. Like environment modeling is hard because environment might be changing, but maybe certain type of tasks like small batch operation task, drilling, polishing, cutting, you may have some environment model for those. Then we can maybe do the simulations. That's what you're saying, I assume. So we can run the simulations, reinforcement simulations on this model, and then once we have some information, then we can move to the real task maybe. Is that what you're saying?
Yeah, I mean, we are always in simulation. But
I see. So, I mean, in our case, simulation is hard because it's not a very deterministic system. Maybe in autonomous driving, it's the same issue. But in like physical human-robot interaction, it's even like harder to generalize, because when you do cutting, you do different human force, different environment. When you do polishing, again, it's a bit different. Although you can divide it into 3 subtasks in general, like idle, free motion, contact, you can generalize it like this, but modeling is still a bit hard. And like depends on the model, also the material that you're cutting, for example, right? If you have a soft material, then the model will be different. If it is a hard material, it's going to be different. So I don't know. I think maybe, is it more well-defined in the case of autonomous driving, the human behavior?
I mean,
can it be better defined?
Agent behavior, you mean? Not
agent behavior.
I mean, there are certain things that you're not supposed to do, like do not hit other cars, do not pedestrian, stop at the red light. These kind of things are penalized heavily. But other than that, follow like the high-level commands are very discrete, like follow the lane, turn left, turn right.
There are some rules, right, in case of driving, but in here, like there are no clear rules. I mean, if I ask you to, for example, do the drilling, I can't put some rules to you. Like I cannot say that go slow, hard, apply more pressure. I mean, so I don't know. I mean, we don't exactly know how we can really model this behavior. We will try, but I think it's going to be still hard.
Actually, Hocam, environment modeling is not that hard because there's always a finite set of different materials with different shapes that you're ever going to try an operation on, and we can just test, and there are many different methods to estimate their impedances, right? So
but you're talking task specific, Pouya, like I mean you can maybe come up with a variety of models for just drilling. But how about like when you go and implement the same idea for polishing?
Well, that's the thing with a single but a single robot in some specific part of the factory is just being dedicated for example, drilling. The same robot is probably not going to do polishing as well. So for every different part of your factory, let's say you have 20 of these different robots. One of them is just for cutting, one of them for drilling, whatever. For the robot that is meant for drilling, you just come up with a selection of 20 different environment impedances. And every time the operator wants to drill on wood, he just selects the wood's impedance and just plugs it in the environment model.
Could be. Yeah, I mean, like you may have a different stations for doing the different tasks. That's a possibility. Yeah, it's a good selling point. We should keep in mind.
Nice. Thanks, Pouya.
Oh, thanks, Hocam. Thank you for listening, actually.